All right, we're going to shift gears into more HPC and sustainable algorithm design with, of course, Professor Jack Dongarra, who's a research professor emeritus in electrical engineering and computer science at the University of Tennessee. Professor Dongarra is a world leader in high-performance computing and numerical algorithms with decades of contributions to exascale computing and AI-enabled scientific simulations. He's also the winner of the ACM Turing Prize. If that wasn't enough, he's also an ADIA Lab advisory board member. So I want to thank him for providing some steering guidance for us over the past 3 years. So Professor Dongarra, of course, will wrap up this session with a talk on high-performance computing, as I said. So please join me.
I hate to be in this position of between us and lunch. Can I get the first slide, please? Yes, that's me. So I'd like to talk about high-performance computing, and hopefully we'll have a chance to talk about some ideas on what I call responsibly reckless algorithms. Okay, so I've been around for a long time dealing with computing. This is probably where I entered in my career, working on a Cray 1. So Cray 1 was a vector computer. Basic operations were done on vectors. And we've seen this incredible change take place over the past 50 years, going from things like vector machines to shared memory computers, to computers that had distributed memory, to massively parallel systems, to Linux clusters, to machines that use that same notion of a cluster, but accelerate them by using GPUs. And you know, the future holds, as is going off the screen, quantum computing and AI. So I'm not a big fan of quantum. I have to say that it's a good research area, but we're not going to see it anytime soon. So it's something to work on and to deal with. AI, of course, is a big deal. It's going to be more important, I think, than the internet has been. So the impact is going to be more important. And I've been in a position to develop algorithms and software that sort of have tried to match those improvements that we've seen in the architectures. So various software packages needed to be created to keep up with the changes that were taking place. So today our high performance systems that we're using are based on commodity processors. So commodity off-the-shelf processors. And that's usually done because we want to keep the cost of the systems low, and we try to obtain what we think is going to be high performance. So we buy commodity processors and put them in our machines. So if we take a look at the top 500 systems, it's a list of the 500 fastest systems. 93% of those machines are using commodity processors. They have an instruction set that came from Intel and AMD. They both share that instruction set, and that's what's used in our machines. 92% of the machines, of the machines that use accelerators, 92% of them use accelerators from NVIDIA. So again, another thing we consider commodity interconnects. 85% of the machines are using either Ethernet or InfiniBand interconnect. Again, off the shelf, just take something which is relatively cheap and put it together inside of a machine. And everything, of course, is using Linux as the operating system. That's different than what we see from the hyperscalers. So the cloud-based systems are designing their own processors to match the needs of their customers. So they're building their own systems. They're investing in hardware. They're building the things from the ground up, where in scientific computing, we don't have the luxury of doing that. Early on, it turned out that there was a good match between the memory speeds and the processors. So if we go back and take a look at the machines that were around in the late 70s, there was a one-to-one relationship between moving a piece of data and doing a computation. So they were balanced. You would take, let's say, 1 cycle to move and 1 cycle to do the computation. As things progressed, as the machines got more sophisticated, we saw changes taking place in that, so that the the ratio from floating point operations to movement of data has changed quite dramatically. So today, there's roughly a factor of 200 between the speed at which you can do the computation and the rate at which you can move the data. So it takes 200 times more to move data than it does to do the floating point operations. So we have tremendous floating point capability, but we can't get the data to the place where the computation is done. And that leads to a lot of performance issues, as you might guess. The cloud providers are designing their own hardware. So companies like Alibaba, Amazon, Google, Microsoft, they're designing their own chips. Those chips go into their products, and you can't buy those chips. You could buy the services on those chips. So they're selling you service, and those chips there that they're providing in their machines are going to make their operations faster. They're not doing commodity stuff. They're designing their own machines. And they can do that in some sense because of the tremendous wealth that they have. And this is bleeding over to the AI companies as well. They're designing processors that meet the needs of the AI side. So what I've got here is the market capitalization for various companies. So market capitalization is what is the company worth? Think of it that way. So if we take a look at I just pulled this data a couple weeks ago, October 18th, so this is relatively recent. So the market cap here says that companies like HPE, Fujitsu, Intel, IBM, and AMD, they provide processors that are used in our high performance machines in most of our computing systems. That's the market cap that they have. Broadcom is an outlier in some sense. Broadcom does networks, they do routers, they do interfaces that move data, and they have a large market cap. A lot of companies use them. If we take a look at the cloud providers, the hyperscalers, we see this story in terms of the market cap. So the cloud providers have this incredible wealth associated with them. Companies in the States like Facebook, Amazon, Google, Apple, and Microsoft, they have this incredible market cap. And not far behind are companies in China, Alibaba, Baidu, Tencent, and Huawei. Those companies perhaps can catch up, but just incredible. Now there's one company missing. Which company is that? NVIDIA. So NVIDIA's market cap is about 4.5 trillion, thank you. $4.5 trillion is the market cap for that one company. And you can see how it really eclipses most of the conventional computing companies in terms of what they're worth. And that, of course, is driven by the AI situation that we find ourselves in today. So this is a list of the top 10 computers according to the top 500 list. The top 500 list says run this benchmark on your computer. We're going to compute the time that it takes you to compute that benchmark, and then we turn that into a rate of execution. So the number one computer today is a machine at the Department of Energy Laboratory in Lawrence, Livermore called El Capitan. It's based on processors that come from AMD. It's integrated by HPE. So HPE doesn't make processors. They integrate, they put things together and sell you a system. So it's using an AMD processor, which has a conventional architecture and then also has a GPU, an accelerator that AMD provides. That machine has 11 million cores. So if you're going to use that machine at scale, and it's intended to be used at scale, you would have to orchestrate those 11 million cores to do your application. The machine on the benchmark ran at 1.7 exaflops, 1.7 times 10 to the 18 operations per second. I have a hard time with that number. That's a billion operations per second. So they're doing 1.7 billion operations per second. And that was 63% of the theoretical peak performance. So they left some on the floor. And the power consumption's 30 megawatts. So what's a megawatt? In Tennessee, where I live, if I use a megawatt at my home for 1 year, I'll get a bill for $1 million. So in Tennessee, a megawatt year is $1 million. So that machine cost about $30 million just to turn it on. So the three machines at the top there each cost $600 million. So they're part of the Department of Energy's exascale computing program. Those are the three exascale computers that we have. And as you heard earlier in the previous presentation, Germany has a machine which is expected to be at exascale on the next list, which is going to come out in November. Just going down the list, US has 4 machines, Italy has a couple, Switzerland, Japan, and Germany. And notably absent is China. So China stopped reporting benchmark numbers. They stopped reporting numbers because the US was taking sanctions, had sanctions against technology going to China. So they decided not to advertise or brag about their machines, and they're no longer playing this game. But they have at least 3 and maybe 4 exascale machines in China that we know about. Okay, and this is, so I said there are 500 machines on this list of the top 500. That's the fastest one, so the y-axis here is the rate of execution. And El Capitan's the fastest, Frontier's the second, Aurora, and down the line here, down to the 500. So you see this long hockey stick effect going out there. Here in the Emirates, there are 4 machines on the list, 4 machines, and the highest one is around 30, around 35 maybe. And 3 of the 4 are associated with G42. So G42 is a company here in the Emirates which is doing a lot of AI-related work and is using a lot of those computers. This is a list of the machines that were number 1 over time. So the El Capitan's the one up in the top right. And back when we started doing this in 1993, there was a machine called this Thinking Machine CM5, which was at Los Alamos National Laboratory, and it was number 1. So you can see I've colored things. Black is the US, green is Japan, and red is China. So China has had a few number 1 machines, and again, they've stopped reporting, so we don't know exactly where they place in this list. But we have, so back in 1997, we reached a teraflop in terms of computing. About 11 years later, we got 3 orders of magnitude improvement with another machine. So running at a petaflop was a machine called Roadrunner. And then finally, we came to exaflop, that 10 to the 18 number, 14 years after that threshold. And the question is, when will we get to zettaflop, another 3 orders of magnitude? And it's going to be longer than 14 years to get to that point. Okay, this is the biggest machine that I know about. It's a machine that Elon Musk has in Tennessee. It's a machine that's built on NVIDIA accelerators. He's using it for AI purposes and training of his chatbot. It's an incredible machine. It has 200,000 NVIDIA GPUs in it, H100s. Those are the previous generation accelerators. It cost about $3 to $4 billion for that machine. Remember I said the DOE is investing in machines, each one about $600 million. This machine is about $3 billion, incredible difference. And the power consumption is 300 megawatts. 300 megawatts, that's just to turn the machine on, would be about $300 million a year. So very expensive machine. And of course, there are plans underway for a new machine. So his next machine is under development today, and that's going to use the current generation of accelerators, and that'll have roughly 500,000 of those accelerators, and the cost of that machine is about an order of magnitude more than what he paid for this machine. So, 2 orders of magnitude more. So it's between $30 and $45 billion for that machine. That's one computer costing $30 to $45 billion. Incredible. So this is just comparing the machines and looking at the machines that I would say are used for scientific purposes. Traditional scientific purposes are the machines at the top here, and this is the European machine which just came into existence. And this is the Colossus machine, the one that Elon Musk has. And you see the difference in terms of power requirements and also in terms of the size of the machine. And this is, again, used for AI purposes. What we see is that there's incredible power demands, as was mentioned earlier. The power demands are such that these companies, the hyperscalers, the cloud-based systems, are turning to nuclear power to fuel them. So Meta, Facebook, is buying the output from a nuclear power plant starting in 2027 to fire up its efforts. Google is committed to a number of these small modular reactors to help provide power for its systems. Microsoft has agreed to purchase power from one of the 3 Mile Island systems that have come online. So incredible power demands from these computing systems, and that's only going to grow into the future. I want to talk about floating point traditional scientific computing. So IEEE has a standard for doing arithmetic. That standard says that there's a format for doing 128-bit floating point arithmetic. 64-bit and 32-bit is what we normally think about in terms of traditional scientific computing. It also supplies a 16-bit floating point format. So the way to read this is there are 52 bits for the fraction, for the precision, and 11 bits for the exponent of a number. And that's just this way we do business with computing. Google says, this IEEE standard, which provides 16-bit mechanisms, the exponent range is too small. So they decided they're going to have their own standard. So Google said they're going to have 8 bits associated with the exponent. The problem with 5 bits in the exponent is a number that's larger than 65,000 causes an overflow. So the dynamic range of the numbers is not great enough to supply that. So Google is using a format called BF16 that now has become a de facto standard. All manufacturers do BF16 in terms of their hardware. And that's used for machine learning and neural networks mainly. NVIDIA says, forget that. We could do a little bit better for our AI friends. So they have formats that use 8-bit floating point arithmetic. So they have two ways of doing 8-bit. One that has 5 bits for the exponent and another that has 4 bits. And so it has 2 bits for the mantissa, or for the accuracy, or 3 bits for the accuracy. And that's used in transformers, the process that we think about for large language models. The forward propagation through a neural network requires higher precision. So that's why they get this combination here. And then the back propagation, the thing that helps in terms of updating the weights, they don't need as much precision, so they can get by with a little bit less. So NVIDIA provides this in the hardware. So they have hardware support specifically for that. And they also have support for 4-bit floating point operations. 2 bits for the exponent and only 1 digit for the representation of the numbers. So from my standpoint, I want to understand if we can leverage some of these things here in our numerical computations. As you go down in precision, things run a lot faster. You usually get a factor of 2. So if I can get by with 32-bit arithmetic, I run twice as fast. Not only that, but I move less data. So I get a benefit, a boost, because I get the benefit of moving data as well. If I can do 16-bit arithmetic, I get another factor of 2, and so on. So can we, in fact, use lower precision to do our scientific computations? We might as well try to use that. And here's an example. This is on an NVIDIA part. This is on a GPU. We're doing matrix multiply. Multiply 2 matrices together. This is the performance I get. If I change the size of the problem, it stays more or less constant. And this is the performance I see. So it's below 100 teraflops in terms of the performance. If I can get by with 16-bit arithmetic, the performance jumps up so I can get roughly 800 teraflops in terms of the performance. So again, if I can use lower precision, I might be able to run a lot faster in terms of the performance. This is just for matrix multiply. your performance may vary. So that we want to look at mixed precision. It reduces memory traffic, reduces the network traffic, it reduces the memory footprint of the application, and the arithmetic just runs faster. So it may be suitable for some problems, and that's really what we want to explore and see if we can get by with that. So we're seeing mixed precision in a lot of the climate models now. So mixed precision, usually 32-bit arithmetic, is finding its way into the climate models because it can run faster. And these models here are in various stages of using 32-bit arithmetic to help boost the performance that they see from those models. So the idea with Reckless Responsible is we want to try a fast algorithm, and that algorithm may be unstable. And it may fail, but we hope rarely. So we want to try something which has the potential to fail, but we want to be able to capture this avoiding data movement. That's one of the things we'd like to do. Avoiding synchronization of the parallel processing, and then use mixed precision to help boost the performance. So those are ways in which we're going to accelerate the performance, if you will, by using a fast algorithm that has these characteristics, but it may fail occasionally. So we have to check. We have to check to see that it's not failed. If it's failed, then we have to abort the computation and start over with perhaps a method which is stable and allows us to compute a solution, but it may be a lot slower. So we hope it doesn't fail very often, but we need to have that check built into it. So that's the responsible part of this reckless behavior. So again, if we need to, we'll go and recompute something. This is a standard operation. It's called a fused multiply add. All computers have this. Fused multiply add has 3 inputs. You take 2 of them and multiply them together. You add in another operand, and you produce a result. So that's a basic hardware operation on the computer, fused multiply add. The GPUs provide an operation which does matrix multiply. That's a fundamental operation. That's what when you hear the word tensor cores, the word tensor is reflecting the fact that it's doing a matrix multiply, not that it's doing a mathematical tensor, it's doing a matrix multiply. So I'm taking 2 matrices, multiplying them together, and adding another matrix to it. So again, similar pattern that we have here, but it does this on a lot of data simultaneously. So we can leverage that matrix multiply power of n-cubed operations and n-squared pieces of data. That's basically what's happening there. So think of it in this way in a cartoon. Got 2 matrices, multiplying them together. There's hardware support for that, so it happens with 1 instruction carried out on the machine, and it can be optimized to be very efficient. If we take a look at what NVIDIA's done, this is looking at two processors from NVIDIA. This is the old processor called Hopper, and this is the new processor called Blackwell. And I've marked here the various, so they have this FMA instruction. That's the scalar version, 3 inputs, 1 output, multiply, and then do the addition. And also the tensor core. So you could see here from the Hopper, this is the performance we get from doing the FMA instruction, and this is the performance we get from doing the fused tensor core operation. So there's a factor of 2 there in terms of the going from the simple to the matrix multiply. For 16-bit operations, they have the same thing. So you see the advantage here of using 16-bit over 64-bit floating point. There's a tremendous advantage in doing that. The newer processor, called Blackwell, notice that 64-bit FMA and the 64-bit tensor core are the same. So they don't have hardware support for doing the matrix multiply for 64-bit operations. If you ask them why, the basic reason is they didn't have real estate on the chip to do tensor cores for 64-bit operations. So I think this is going to be a trend that we see, and the trend is that 64-bit may go away in terms of hardware support because AI doesn't need it. AI needs short precision, so we'll see more effort being placed in terms of doing the shorter precision. And you could see that here, 16-bit is a lot faster, and if you can get away with this integer operations, it's even really fast, integer operations. So there's a factor there a considerable factor improvement, 2 orders of magnitude if you could do integer operations. So there's a lot of activity today in doing integer operations to do our numerical floating point work. That is, can we use that hardware to do floating point computations? Can we use the integer hardware to do floating point computations? So if we think about that just briefly, if we're going to take two numbers and add them to multiply 2 numbers together and add a third number, I'm going to represent those numbers in terms of some fraction and then an exponent. So I can do that for any numbers, represent them in terms of that. And then if I think about those as being slices of the number, and what's the impact of taking those slices and multiplying them together? So I've just taken this equation and multiplied by this one, and this is sort of the mess I get out of that. And that mess I can do in integer operations. That is, I can represent these as integers, A naught and B naught, multiply them together using that very fast hardware, and remember the exponent I had associated with it, and then carry out these additions. So this is a way in which you could use that hardware. And some of these operations even get too small so we can ignore them, and we end up with a situation where we don't want to do it with those operations, we want to do them on matrices. So I take my data and I take the information in these matrices and put them into what I'll call bins, where each bin has the same exponent associated with it. So we have numbers which have the same exponent, and we can then just represent the number as integer parts. So I do that, in this case here, I have 3 bins. I've taken my matrix and sliced it so that I can represent it into these 3 bins here. And then I think about multiplying those matrices together and coming up with a appropriate operation, and then finally putting them together to get the floating point representation. So that algorithm is being championed by a group in Japan, and since they've shown how effective it can be, a lot of people have become interested in doing this fixed point arithmetic using the integer units and leveraging that with the performance. And just to give a sense of how much faster things are, this is looking at various representations. The slices here are the bins I have associated with the numbers. If I can get by with 5 bins, things can run really fast. If I have to go to 9 bins, things slow down considerably. And I'm looking at the speed up over doing what would be considered the standard 64-bit floating point representation. So there's an algorithm which uses that hardware that does the integer tensor cores to do these matrix multiplications. And if you can get away with it, you can end up with something which is 5 times faster than what you can do using the built-in 64-bit representation of those numbers. But we have to be careful, because if the numbers that we have run out of these bins, the exponentials that we can sort of sort things in, the algorithm will fail. And we have to be prepared to understand that failure. And so we have to analyze the input data, and we have to either carry out the operations with that emulated matrix multiply, or we abort the operation because we can't represent the data in with the algorithm that we have and start over again. So that's the recklessly responsible part of that algorithm. So the algorithm was done by a guy named Ozaki in Japan. There's been a number of papers published about it, about how well it can do, and it's caused a fair amount of excitement in the community to try to utilize that integer arithmetic. And there's a paper that we did to try to analyze the numerical aspects of the operations. So the Ozaki scheme offers an effective method for computing the product of these guys using integer operations. The input matrix are divided into these slices and then multiplied together. And there are some problems with the algorithm, and that one has to be aware of those issues. Okay, so we're about to go for lunch. So the takeaway here is, the hardware is constantly changing: scalar, vector, distributed memory, accelerators, and mixed precision. The hardware and the algorithms and software always follow the the hardware advances. That's something to remember. Follow the hardware advances in that it takes a long time when we get a new architecture to really take our existing stuff and move it to that new hardware and get the benefits of it. And there's plenty of room at the top. In other words, there's plenty of room to optimize. I'll send you to a paper that I found very interesting. Charles Leiserson wrote this paper with his colleagues a few years ago. There's plenty of room at the top that will drive performance after Moore's law. And he's talking about software algorithms and architectures and how one can effectively use them and increase the performance. And it's a riff on Feynman's classic lecture that he had that said there's plenty of room at the bottom, which talked about quantum computing and its things. So I'll leave you there. I'm happy to answer any questions. Thanks for your attention. Oh,
Just one question. Just one question.
One question, because we're all hungry. Yes.
Hi, Jack. Thank you very much for a very engaging presentation. Just from your professional network and your daily engagements with experts in the field, are you seeing any progress from the hyperscalers in their own chip development where potentially they can challenge the monopoly that NVIDIA seems to have carved out? Obviously high margin, but be interested to get your insight about whether they're close or there's a potential they might start building their own challenger chips.
They're doing it. They're building their own machines. They're not only the processors like the GPUs, but also the networks. They have specialized networks to allow them to pass data around very, very effectively. So again, those things are not for sale. Those are things that they use internally and they develop, and they have. You take a look at Google's TPUs. That's a good example of a GPU-like thing, which is designed and being used internally for their hardware. And you can use it. You can buy time on it, but you can't buy the actual hardware. And I think that'll continue as going forward.
Thank you.
Okay, it's lunchtime.
All right, thanks, Jack. We'll reconvene at 2. So I know many of us have missed all the parallel sessions that are happening, but we'll have a panel there, which Adam will be on representing this session, and we'll have 2 others from each of the other 2 sessions to summarize what happened in those sessions as well. So I'll let you break for lunch. Last round of applause for our speakers.